is that the points on a line segment can be put into a one-to-one correspondence with real numbers. Essentially, you can take a line segment and put the points in a correspondence to a ruler and measure it. So line segments are measurable. And then the segment addition postulate says that if A, B, and C are collinear, point B is between A and C if and only if AB plus BC equals AC. And that's just basically telling me that if I have 3 points, A, B, and C, this part is AB, this part is BC, and the whole thing together is AC, so AB plus BC equals AC, which we kind of already knew. But what the postulate is telling me is that it won't be like B, A, and C, because then AB and BC wouldn't equal AC. Does that make sense? So they have to go in that order for that to work. Oh, wow, that eraser was way too big. And that one's way too small. The postulates and theorems we already have with our new segment addition postulate to prove that if these two things are congruent, then this part's congruent. So basically what we've got is CE and FE are congruent. So the two little parts are congruent. And then EG and ED are congruent as well. And we're going to try to prove that because the two little parts are congruent and the two big parts are congruent, that if I take these two pieces and stick them together, they're the same size as these two pieces stuck together. So this plus this equals that plus that. Okay, that's what I'm trying to prove. So I've got my statements and reasons, and I need to move that up a little. So statements, reasons, and I'm going to start with the given. Now, up until this point, we've put the given on two separate lines every time. If your given statements are short enough and you want to stick them on the same line, you can do so, like that. Of course, you probably want to make your congruent look like an actual congruent and not some wonky, I don't even know what that was. Okay, so CE is congruent to FE, ED is congruent to EG, those were given. Okay. Well, what does that mean if you're congruent? Equal. Congruent is equal. So I'm going to take CE, and I'm going to write it in nicer handwriting, sorry guys. CE is equal to FE, and ED is equal to EG. That shouldn't have lines over top of them. Okay, when you don't have the line, you're talking about the length of, when you do have the line, you're talking about the actual piece. So this is the length of CE equal to the length of FE, and the length of ED is equal to the length of EG, and that's the definition of congruent. And you can write out the words, or you can use these lovely abbreviations and symbols and be shorter. Okay. So now I've put that the two small pieces are the same size and the two big pieces are the same size, and I want to make the big pieces, right? I want to make the whole thing. So I add them together. So CE plus ED equals CD. And FE plus EG equals FG. And both of these are segment addition. Okay, because I add two small pieces to get a big piece. Or two parts make up the whole. So I added CE and ED and got CD. And then I added FG, E and EG and got FG. that's great. So I've got little pieces that are the same size, medium-sized pieces that are the same size. I've added small and medium to get large. And now I need to show that the larges are the same size. So what I'm going to do is, these two are the same size and these two are the same size. So I'm going to substitute. And I'm going to say that CE plus ED is equal to FG, because I can take those out and put those in and it's the same length. Like this is 1 plus 3 equals 5, and this is 1 plus 3 equals 5 also. They're the same length. So I can exchange them. That's substitution. And then, since I did that, because these two together equaled CD and now they equal FG, I can take these parts out and put those parts in. That's also substitution. And that's the definition of congruent. And that's what I was trying to prove. Now to get to this, the first bit will be the same. So definition of congruent. And what I might do is, instead of adding them together to make the big piece, I might say that CE plus ED is equal to CE plus FE. I'm writing the same thing twice and I don't mean to do that. FE plus ED. Yeah. Because I'm allowed to add the same thing to both sides, right? So I could have added EG to both sides, or I can add ED to both sides, because that's just addition. And I'm allowed to add whatever I want to both sides of anything at any time. So that's addition. And then I can say, that's an E. ED and EG are the same, so I can take ED out and put EG in, and that's substitution. Okay, and CE plus ED is equal to CD, and FE plus EG is equal to FG. That's segment addition. Does that make sense so far? So I add ED to both sides, I take ED out and put EG in, add the pieces together, get the big bits, and since they were equal, they're congruent. Actually, it's not a beast. We've got JL is congruent to KM, that's given. So JL, that's this whole thing right here, is congruent to KM, this whole bit right here. Okay. So these two are the same length, and I guess I didn't put the points in, so I'll put them in right now. Okay. And we want to say that JK, this little part, is the same size as this little part. Okay, and this is also just one way to get there. But because they're congruent, that means they're equal. That's the definition of congruent. Okay, JK plus KL equals JL. That's segment addition. KL plus LM equals KM. That's the segment addition also. Now, I knew that JL and KM were equal, so now I can say that JK plus KL and KL plus LM are equal with substitution. Right, so I take these two out and put these two in. And I'm trying to get to JK and LM, So I can see how I can take out these KLs that match. So I subtract KL from both sides in that subtraction. Except, with a 5 instead of an S. And once I've subtracted the KLs, those two cancel and those two cancel. So I've got JK is equal to LM. And then once they're equal, they're congruent. And again, that's not the only way to get K. JL equals KM. Definition of congruent. I can say that KL equals itself. Reflexive property. And since it equals itself, I can subtract it from both sides. That's just subtraction. Okay. JL minus KL is JK. KM minus KL is LM. Right, LM? Yeah, LM. Okay, now this is the part where it seems kind of backwards, but it's called segment addition. Even though I'm subtracting a piece, we don't have a segment subtraction property, we just have segment addition, so we're adding a negative. We're using that same property, we're just using it backwards. And since they're equal, they are congruent. Definition of congruent. We did these, I kind of went over them, but we talked about, you have reflexive of equality. It's the same as congruence. So like if AB is congruent to itself, that's reflexive property. So you can take out the equal sign and put in a congruent symbol, and it's the same property, same thing. So symmetric is if AB is congruent to CD. I can flip congruence as well as flip around an equal. I can flip around a congruent symbol, which is the same. Or if I have AB is congruent to CD and CD is congruent to EF, then AB will be congruent to EF. So I can also do transitive through congruence. And I can do substitution with congruence, addition, subtraction, all of the properties still hold true for congruence. Statements and reasons. And that X is the midpoint of SY and Z is the midpoint of YF, and XY is equal to YZ, all three is given. And from our pictures, XY is equal to YZ, and then X and Z are midpoints. As far, what does it mean to be a midpoint? It's in the center, right? So if X is the midpoint of SY, that makes SX equal to XY. And if Z is the midpoint of YF, that makes YZ equal to ZF. So those are the definition of midpoint. Okay. Now I already knew that XY and YZ are equal. So I can replace them, right? So XY is equal to SX and YZ is equal to ZF, and they're equal to each other, so I can take the SX and replace the XY, and I can take the Z f and replace the yz because they're equal. And that's just substitution. And because they're equal, they're congruent. And I wanted ZF in front, so I can move them because of symmetric property.